This video should put deriving equations for projectiles in a nutshell. I'll look at those launched horizontally as well as those launched at an angle. For horizontally launched projectiles, we will make a couple of assumptions. For example, the base will be directly beneath where the object launches from. Also, that gravity will be working in the down direction at a negative 10 meters per second squared, and that the initial velocity is only in the x direction, and only after it begins falling under the force of gravity does it acquire a y component to the vector of velocity. Also, if we choose to measure the height from the top down in the direction of motion, that's going to be a negative quantity, which actually helps in our equations. All right, let's look at the derived equations. Because there is no vertical component to the initial velocity as the object is launched horizontally, then we can take this equation and rearrange it to solve for time, which will be the square root of 2 times the height, y, divided by gravity. If you measure height downward and it's negative, and gravity works downward, negative, the two negatives cancel each other out, so there's not a problem with the sign of the value under the square root. With these problems, we want to always solve for time first, because we will use time to find everything else. If the initial velocity given of the launch projectile is in the horizontal direction, then we can find the range x by taking and rearranging this equation. So we'll take the given velocity times the time that we just calculated for the horizontal range. If we next take this equation and consider it in the vertical, and with the same assumption that there is no initial y velocity, then we can use this equation to solve for the y component of the final velocity by multiplying gravity times time. This will give us a negative answer, but since it's working in a downward direction as the object falls, that's okay. The negative will be talking about the direction. Now that we have the vertical component of velocity and we're given the horizontal component of velocity, we can then treat that as a vector and do Pythagorean theorem to get the magnitude of the velocity, and we can also do tangent of theta to get the direction. Now let's look at some of the basic assumptions about projectiles launched at an angle. First, the angle with which it is launched is equal to the angle with which it lands, but in the opposite direction. Likewise, the velocity with which it is launched is equal to the velocity with which it lands, but in the opposite direction. Velocity, being a vector, has a y component, vertical, as well as an x component, horizontal. Notice that according to this diagram, that changes during the path of the projectile. And at the apex, there is no vertical component, because at this point, the projectile has to stop going up and start falling down. It's at this midpoint that we can calculate the maximum height of the projectile, which occurs at the half-time mark. Also, looking at this diagram, we can tell that the position where the object lands is lateral to the position where it was launched from, and so we can also say that the change in height from start to finish is 0 because it basically lands back where it began. These assumptions lead us to derive the equations. In the problems we've been given, we've typically been given the magnitude and the direction of the velocity vector. So step 1 is to resolve that into horizontal and vertical components. These components are critical in the other calculations from the derived equations. In order to find the range, we'll take the original velocity equation and rearrange to solve for x, using the horizontal component of the velocity vector. And in order to do this, we're going to need the calculation for time. Let's use this equation to solve for time, but we're going to make a different assumption about what is equal to 0. This time we're going to say it's the displacement that's equal to 0, delta y. So the equation becomes t is equal to negative 2 times the vertical component of the initial velocity divided by gravity at negative 10 meters per second squared. That way the negatives cancel out. To find the maximum height of the projectile, we'll take this equation, but assume that the final velocity in the y direction at the apex is equal to 0. The equation looks like this. By dividing by 4, we take into account that at the maximum height, we've only reached half of the time sequence. So this will give you the maximum height.